Okay, so with this position versus time graph, okay, remember that what I can read directly off of it is where the object is at various points in time. If I know where the object is at various points in time, I should be able to figure out its displacement, its distance, its velocity, and its speed, okay? And the reason for that is that I will always have on this graph the ability to calculate or read all the parts of this formula, because really this formula is this, right? And I can read position and time directly off of this graph, okay? And I can use this to get distance as well, which means if I have distance, I should be able to calculate speed also, because I'd be able to fill in those formulas, okay? Would I be able to use this formula on this graph? I don't have velocity on this graph. Okay? I can't use this formula. I might be able to determine whether something is accelerating or not, but I wouldn't be able to calculate it given what we know so far. There's actually ways that you learn them later on in physics. Okay, so what's the displacement between 4 seconds and 15 seconds? Okay, well, I know that I can calculate displacement with this formula if I have v, but I don't have it. But I can also calculate displacement by taking the final position and subtracting the initial position. So that's what I want to do. Are you following here that I didn't memorize? I didn't just go straight to do this. I went to, what do I have? What am I looking for? How can I get what I'm looking for with what I have? That's the process I want you to go through on every graph. Because if you're memorizing, you're going to get it wrong on the test. You're going to mess up some part of it, okay? As opposed to, what do I have? This is kind of like writing down our givens on a word problem. What do I have on this graph? I have position. I can figure out where this object is anytime I want to, as long as it's on the graph. Well, that's good. That's like having those for givens, okay? And then I can go into a formula from there. Does everyone kind of follow? Okay? It's better to have the process than to memorize things. Okay. So between 4 seconds and 15 seconds. So at time 4 seconds, okay, I'm at a position of negative 10 meters. So that would be my initial position. And at time 15 seconds, I'm at a position of negative 1 meter. All right, so that means if I want to find the displacement, I'm going to go final position minus initial position, and that's going to be negative 1 minus negative 10. Okay, so negative 1 minus negative 10 should be positive 9 meters. Okay, well that makes sense. I did go from here to there. That is positive 9 meters. That's 9 meters forward of where I started. Everybody okay with that? Okay. What is the total distance traveled? Okay. So distance is how far I go. Doesn't care which direction, doesn't care whether I've turned around, okay? Just cares how far did I go. Can I figure out how far this object travels in each part of the graph? Okay? Is that different than me just going final position minus initial position? It is. If I do that, I'm calculating the total what? Displacement. That would be the total change in position, because that's what I'd be using. But if I want to calculate the distance, that means every time the object moves, which means I have to be able to identify when it's actually moving, okay? I just need to figure out how far it goes every time it moves. Is it moving here? Okay. Is it moving at a constant velocity here? It is. Okay, so then I'm going to go final position, 10, minus initial position, 20. Okay, that's 10 meters. Am I moving here? Nope. Okay, during this part it's flat. Position's not changing, so there's no movement there. Okay, and then in this part I'm moving again. I go from negative 10 to positive 14. Right? And I'm just doing the final position minus initial position math in my head here. Okay? But from negative 10 to positive 14 is 24 meters. Is everyone okay with that? Okay. Am I moving here? All right. And then I'm moving here because my position is changing again. And I go from 14 down to -1. So that should be 15 meters. Okay? All right, can I now calculate the total distance? All right, what do I do with those numbers? I just add them up, yeah. Okay, so we got 34 plus 15 should be 49 meters, yeah? Okay, that's what we do there, all right? And again, it's not a matter of memorizing. What I have memorized and what is important to memorize are the definitions of things. What is displacement? Displacement is change in position. What is velocity? Velocity is the rate of change of position. Those things I have to memorize because that helps me to go, what can I do on this graph? Okay, but I don't want to memorize that. I calculate displacement by finding the area of shapes. Do I do that on this graph? I don't. And then I might accidentally do it on this graph, and then it's not calculating the right thing. Okay, so I don't want to memorize things. All right, number 3, what is the average velocity over the whole trip? Okay, so average velocity, I just wrote the formula down here, is total displacement divided by total time. And I can get displacement by going final position minus initial position. Perfect, I got all those things on this graph. Okay, so V is going to equal, okay, my final position, -1, minus my initial position, -20. Okay, and I'm going to divide that by 15 seconds because that's how long the whole trip takes. Okay, so -1 minus -20 should be 19. Okay, positive 19. And divide that by 15 seconds. All right, so we're looking at 1.3 meters per second. Positive 1.3 meters per second. Okay, everybody all right with that? Okay, once again, it was just a matter of I have this formula has what's on my graph, boom, here I go. Okay. All right, for number 4, what is the average speed between 0 and 10 seconds? What do I do differently?
Don't count negatives.
Right, I don't count negatives. Speed is distance divided by time. So I need to know how far does the object go between 0 and 10 seconds. Okay, well, it goes 10 meters, and then it goes 24 meters, and 10 seconds is right here, so 34 meters is what it looks like to me. Everyone okay with that? Okay. So, speed equals distance divided by time. Okay, that's going to be 34 meters divided by 10 seconds. Okay, and that's going to be 3.4 meters per second. No positive on that, it's scalar. Okay? Everybody all right with that? Okay. Any questions on this graph? That's a pretty typical position versus time graphing question. Okay. The only other thing I might throw in there would be this, and I think we talked about this yesterday. What's the acceleration of this object between 10 and 15 seconds? Why? Why is it 0?
It's a constant velocity, so there's no change in velocity.
Right, there's no change in velocity during that time. There's a change in position during that time. This is a position time graph. That's that interpretation thing. Okay? In this case, every second it goes the same distance. Okay, so if I'm looking at this here, okay, during this first second it went that far, during the next second it went the same distance, during the next second it went the same distance. Okay, every single time it went -3 meters every second. Right? Didn't change its velocity. That's another one where I'm doing some interpreting, but I'm also using the definition of acceleration that I memorized. Okay? Acceleration is any change in velocity. Between 10 and 15 seconds, there is no change in velocity. Okay? How many marks would that question be out of? 1. That's it. 1 mark. Okay? We wouldn't have to do any work. It's a recognition question. Now, what if that section of the graph looked like this? Would it be accelerating then? Definitely. Okay. Let's do this. We haven't done a linear velocity time graph yet, so let's have you guys work on this. I'm going to give you 5 to 10 on this one, and then we'll go through it. All right, so this is a velocity versus time graph. Right off of this graph, I can read how fast and in what direction the object is going at any point in time. And in this case, it looks like it's doing pretty much just one thing. Okay, it's a nice linear graph. And on that graph, I can see that this object is accelerating. Okay, because its velocity is changing over time. Is that also how we calculate velocity? Right? It's the change in velocity over time, right? The rate at which we change our velocity. Okay? Well, here's something to look at, because this first question would be at a 1 mark. Okay? And the reason it's at a 1 mark is because, according to our definition of acceleration, it is the rate at which you change your velocity. Well, on any graph, and velocity is on the y, and time is on the x. Agreed? Okay. On any graph, the slope is the rate at which y changes as a function of x. So on this graph, is the slope the rate at which the velocity changes over time? It is, without me having to go and find these numbers. I can just look right here and know that that 4.82 meters per second squared is the rate at which the velocity is changing. Okay? Did that require me to memorize anything other than the definition of acceleration? It just required me to look at my graph and go, what's here, and what does slope always represent? Okay? That's, again, that danger of memorizing. On this graph, slope is this, and on this graph, slope is this. I don't want to do that. I want to memorize that slope is how fast y changes over x. And if on this graph, y is velocity and x is time, then the slope is acceleration. Okay? I got to work that out in my head on every graph. Okay? All right, so we already know the acceleration is positive 4.82 meters per second squared. What's the initial velocity of this object? Initial velocity would be how fast and in what direction I'm going at time 0. Okay, so according to this graph, at time 0, the object is moving at positive 5.35 meters per second. Okay, did I have to do any calculating? But I had to remember what initial velocity means. Initial velocity is how fast I'm going at time 0. Okay, well, that I can read right here because the y-intercept is the initial value of y, in this case, velocity. Okay. All right, what's the displacement? This one we got to do a little bit more work for. Okay, we do have to remember, again, that displacement is average velocity times time. Okay, in this graph, we don't start with a velocity of 0. Okay, so that means that the object could have done this and just traveled at a constant velocity for 15 seconds and gone that far, but it's also accelerating. Okay, so I have to calculate its average velocity while accelerating and multiply it by time. In other words, I'm getting the areas of these two shapes. Is everyone okay with that? Okay, now, did I memorize that the area was displacement? No, I talked myself through what process I needed to do. Okay, using what's on the graph. I can get this from the graph. Okay, I can get that from the graph. That's my best bet. All right, so for the lower rectangle there, the height of that rectangle is 5.35 meters per second. The base of that triangle is 15 seconds. Okay, so that means then that that little box is 80.25 meters. Positive 80.25. All right, then I've got the triangle on top of that. I need to calculate the height of that triangle. I already know the base is 15 seconds. So, do I need to know what y is at 15 seconds in order to do that? Okay. Do I right now know what y is at 15 seconds? No, I don't. Can I calculate it? Okay. Can I use the equation of the line to do it? Yeah, because I'm solving for a y value, and I know what x is, 15. Okay. Yeah, use this. Okay, so y is going to equal 4.82 times 15 seconds plus 5.35. Okay, I could save myself a step and not add that 5.35, but we'll do it anyway. Okay, so I'm going to have 5.35 times 15 plus, whoops, sorry, not 5, 4.82. Not 5. 4.82 times 15 plus 5.35. All right, so that's the height of the triangle, or sorry, that's what y is, measured from the x-axis. I only want the height of the triangle. So that means I have to subtract what I just added on, which was 5.35. That's what I said. I could save myself time by just not adding that on there because I'm going to subtract it off in a second anyway. All right, there's the height of my triangle, 72.3 meters per second. That's how much the velocity changes by in 15 seconds. All right, so now that I've got that, now I can go that number divided by 2 times 15 seconds. Height over 2 times 15. Okay, so that's going to be 542.25. Okay, what do I do with those two numbers? What do I do with them? Add them together, yeah. So, plus, oh, where did my 80.25 go? There it is. Okay, so the total displacement is 622.5 meters. Okay, is that the kind of calculation I'd make you do on a test? Absolutely. Okay, that makes you use y equals mx plus b. It makes you use, your knowledge of how a velocity versus time graph works to get the displacement. Absolutely, that's what I would ask you to do. Okay, as are these two questions. This could be one written response question. Okay, with a part A, a part B, a part C, and a part D. And a part D. Okay, number 4. How many people have done number 4? Okay. How long will it take to reach a velocity of 215 meters per second? Okay, how long always means I'm looking for time. Okay, time is on which axis? Okay, so I'm looking for an x value. I'm looking for x when y is 215. Okay, so that means I can go y equals m times x plus b, manipulate for x, so y minus b divided by m equals x. 215 minus 5.35 divided by 2.73, right? No. 4.82. I think it's 2.73 from. Okay, what do I have to be mindful of on my calculator with this calculation?
The subtraction and order of operation.
Right, I got to make sure I bypass order of operations by doing the top first. See? Yeah. Oh, Michaela, go too. Yeah, both of you go. All right, so 215 minus 5.35, not 535, 5.35. Okay, hit the enter button so that that one's done first. Now divide it by 4.82, or I could have done it in brackets either way. Okay, so that's going to take 43.5 seconds. Okay, everybody all right with what I did there? Just use y equals mx plus b. Okay, if I give you a graph and I give you the equation for it, okay, am I going to ask you to use the equation? Yeah. Okay, if I give you a graph and it has the equation for the line, chances are that's what I want you to use. Especially, and this is important, if I do this. In the question I go, using the graph below and its equation in bold-faced, italicized, and underlined font, okay, solve the following, you should definitely use the equation. Because I've probably set it up so that if you do anything else, you'll get it really wrong. Okay, so if I explicitly state I want you to use the equation, use the equation. All right, last one on here. What will the velocity be after 1 minute? We had one like this yesterday. What's the trick with that?
60 seconds.
I need to put it in seconds because my time is in seconds on the graph, right? But I'm just looking for a y value here, right? So I'm going to take my 4.82 okay? I'm gonna multiply it by 60 seconds, 1 minute, okay? And I'm gonna add the initial velocity, 5.35. Whoop, that's 60 plus 5.35. 294.55 meters per second, positive. Okay? Everybody all right with that one? Okay, last thing we're going to do, irregular velocity versus time graph. Okay, so this one was linear, just one linear function. Okay, the last one on your sheet is this, an irregular velocity versus time graph. Okay, can you use most of the same things that you used on the last graph? Right? With the only thing you can't use is y equals mx plus b because you don't have that on this graph. Okay? It does a whole bunch of different things here. All right, give you 5 to 10 on that one and we'll go through it. Okay guys, just so we kind of get through this one, we're just going to walk through it quickly here. Number one, this is a velocity versus time graph. Can I read the velocity directly off of this graph? I can, right? So at time 14 seconds, the velocity is positive 1 meter per second. I can just read it directly off the graph. Okay? What is the acceleration between 16 and 19 seconds? All right, so I got to remember acceleration is BF minus BI over T. Okay, that's how I can calculate acceleration. But I might not need that formula for this part of the graph because this is 16 seconds and this is 19 seconds. What's the object doing there? Moving at a constant velocity of positive 5 meters per second. According to the definition of acceleration, that object's not accelerating. So that would be a 1-mark question, and the answer would be 0. Okay. Number 3, what's the total displacement over the 20-second interval? Okay, well, we got a lot of shapes here. Okay, what we're doing is displacement equals average velocity. Sorry, d equals average velocity times time. For this first part, the average velocity is 3, the base is 2, that's 6. Okay, for this part here, it's accelerating from 3 to 0, so the average velocity is 1.5 times 1 is 1.5. Okay, so I'm just doing the height over 2 and then multiplying by the base. Everybody okay with that? Height over 2 is the average velocity, the base is time. All right, then I've got this triangle here where the object is still accelerating from 0 to -9. So the average velocity would be -4.5, and it does that for 3 seconds, -13.5, I believe, meters on that one. This is meters, that's meters. Okay, and then travels at -9 meters per second for 3 seconds. That's going to be -27 meters. Okay, then it goes from 9 to 0 for this part. Okay, so -4.5 is again the velocity. This time times 1, 2, 3, 4 and a half. 20.25, I think, is 4.5 squared. That's negative. Then I've got this triangle here. Okay, that's 5 high by 2.5 on the base. So 2.5 times 2.5, 5 point something. 6.25. Sorry. Okay, 6.25 meters. That's positive. This box here is 5 by 3, so that's 15. And then this box here is 5 high by 1, so that'll be 2.5 meters. Add those all together, making sure the signs are all the right way, and you've got your displacement. Everybody with me there? I wouldn't give you one that had that many shapes on a test, obviously. Okay? What's the acceleration between 9 and 16 seconds? That's here to here. Now I use that formula. Okay? VF is 5. VI is -9, okay, and that takes from 9 to 16 seconds is 7 seconds. That's actually 14 over 7, so that should be +2 meters per second squared. Okay, and then lastly, average velocity between 0 and 9 seconds. Did we already do most of the work for that? Right, we got all the displacements. add them together, making sure the negatives are negative, and then divide by 9 seconds, and you've got your average velocity. All I did there was know that average velocity is displacement, which I already had, divided by time. Again, it's nothing I memorized. I just walked through each step. I had to do it fast this time, so I didn't walk. I ran through each section. Okay, that's the last of graphing. We're going back to work energy theorem on Monday because work energy theorem is fun. Or at least for a physics geek like me it is. Okay? I'll show you some cool videos of people breaking bricks and sticks and stuff with their hands. That's kinetic energy and working. Okay, so that's what we'll be looking at on Monday. Good job today, guys. Have a good weekend, but not too good.